Today we're talking about antiderivatives. And so suppose f is some function. We can say that capital F, or large F, is an antiderivative for regular f if regular f is the derivative. So if f of x equals the derivative of this capital F for all x. And then this leads us to a relevant fact. If we've got an antiderivative and we add some number to it, it's still going to be an antiderivative, okay? Where for c being any real number. So, the proof would be, okay, if we know that f of x is an antiderivative for smaller f, then it's going to be the case that the derivative of capital F is regular f. Okay. So let's look at the derivative with respect to x of capital F of x plus c, where c is some real number. Okay, we're going to take the derivative of capital F, and that's just the derivative of capital F, plus the derivative of a number is 0. And we know that the derivative of capital F is lowercase f. So that's just going to be f of x, meaning that if the derivative of capital F of x plus c is regular f, then capital F of x plus c is an antiderivative. Okay, here we've got some examples of I'm giving you the derivative, you find me the original. So I'm going to freeze the screen and you can just see if you're doing it right. We did a few of these last time, so it might be something that you're familiar with. Yes, but you don't know that yet. So now we're just solving differential equations. Next unit is where we're going to come back and solve the area question. And the connection between the two is kind of like the big reveal of calculus AB. So we're thinking, can I think of a function that has derivative equal to x squared, or sine x, or 5, or 0? Okay, so what are we thinking for 4x? What kind of antiderivative are we getting for that one? 2x squared. Yeah, we're preparing for the power rule. And so I'll come back to that. And so the same thing with x squared. We're preparing for the power rule, so we're saying what is an antiderivative for x squared? Yeah, x to the third, but divided by 3 to prepare for that 3 coming down when we do the power rule line. Okay, what about sine x? What's an antiderivative for sine x? Yeah, it's not regular cosine x, it's negative cosine x. Okay, cosine has derivative negative sign, so we have to prepare for that negativity by basically dividing by -1, which just ends up making it negative cosine. Okay, 5, we're thinking 5x. But what about 0? What's an antiderivative for 0? Yeah, the 3, some constant, some number. We could just call that c. Okay, that's what we're going to do. And so and then I'll show you what I have. So what I did was, saying it could be any number, but you're not wrong if you say 3 is an antiderivative for 0. But you haven't thought of all the possibilities. And so that's why we add the plus c to all of our antiderivatives, because of that fact that I showed you, just a moment ago. Okay, so let's formalize this reverse power rule. So we remember that, and from the beginning, we've been taking derivatives of polynomials, and how we did that was we started by multiplied by the power of x that we have, and then we reduce the power by 1. So if we do this in reverse, we're going to have to undo our steps. And so kind of like, if you're driving to the store and you take a right turn and then you go straight and then you take 2 left turns, when you're on the way back, you're going to have to take 2 right turns, then go straight for a while, and then take a left turn. So we're going to have to reverse the steps and reverse the order. Okay, so the reverse power rule is going to be increase the power by 1, and then divide by the new power. Okay, so we've got some basic antidifferentiation rules. So if we have, f of x equals 0, an antiderivative of 0 is just some number, c. Okay, we already talked about that. If we have the antiderivative of a number, where k is some real number that's presumably not 0, we're going to say that that's kx's and also plus some real number. Okay, an antiderivative for x to the n, where x is some number, is going to be, that's the reverse power rule. So we're going to increase the power by 1. We're going to divide by the new power. And we're not going to forget the plus c. The constant multiple rule. Okay, the constant multiple rule for taking a derivative is you just, keep that constant multiple. You don't have to do the power. You don't have to do the product rule. So the derivative of 5 sine x is 5 cosine x. So an antiderivative of k times g of x is going to be k times an antiderivative of g of x. So I'll just write it like that. And then if we're adding or subtracting, we've already kind of done that just without even thinking about it because derivatives have this linearity to them. Okay, so we're going to say that it's an antiderivative for g plus, or maybe minus, an antiderivative for h. Okay. So why don't you all put that into action on the ones on the right. Then you can check your work against mine. Yes, we'll do that. We'll do that in a few minutes. Yeah. Yes.
So do the capital letters think that's the antiderivative?
Yes, for now, that's what we're, for now, I mean, just for like the next couple of minutes, we're going to use the capital letter to denote the antiderivative. And in general, you will see that sometimes, but that's not as good as we could do it. So yeah, I'll show you very soon. I suspect from your physics class, you already know what we're going to use. Okay. There's the answers. All right, now let's take some antiderivatives of trig functions. Okay, so we already said that an antiderivative of sine x would be negative cosine x. Oh, that's wrong. All right, an antiderivative for cosine x, you think to yourself, what has derivative equal to cosine x? I know, sine x. And you don't forget the plus c. Secant squared x. Okay, so you're not taking the derivative of it. You're thinking to yourself, what could I take the derivative of and get secant squared x? Tangent. Yes, okay, here we go. Okay, so when you think the same thing about secant tangent, okay, secant x times tangent x, that's going to be secant x. And you're not going to forget the plus c. Okay, cosecant squared. That's a little bit tricky, okay? So anybody got a conjecture about that one? Yes, okay. So it kind of like sine, we're going to have to prepare for the negativity by thinking, okay, if I took the derivative of cotangent x, I'd get negative cosecant squared. So, but I don't have cosecant squared, I don't have negative cosecant squared, I have regular cosecant squared. So I need to prepare for that by putting a negative out here and saying negative cotangent x plus c. Cosecant cotangent, same thing. Okay? That's generally, you see that it's got a negative on it. So I'm going to prepare for that by saying negative cosecant x. And I'm not going to forget the plus c. What about tangent x? Can you think of anything that has derivative equal to tangent x? That's the derivative. So the derivative of secant squared, we'd have to do the chain, or the chain rule, power rule. Okay, so that's not one that follows directly from our differentiation rules. And if you look in the course description on AP Central, which I doubt any of you have, but if you do, you see that the antiderivatives you're expected to know at this point in the year. We'll get a product rule for antiderivatives in the spring semester, but the ones that you're supposed to know follow directly from the differentiation rules. This one does not, but it doesn't mean that there doesn't exist one. Yes, question 63. Oh, okay. Yeah. Question retracted. Okay, but so what this is you need to look it up. No, really, I mean, you would look it up in a table of integrals. In the front of your textbook, if you have a hard copy of that, which I know very few of you do, if you do have that, you could open the front cover and you could look up the antiderivative. Or, even better, you could take that device of yours and go to Google and say antiderivative for tangent x. And what you're going to find is, I'm pretty sure it's... And if somebody could check that, that would be nice. I think it's going to be negative log of absolute value cosine x plus c. But that's not something we're expected to memorize. Is that true? Okay. Yeah, I did it yesterday, so I would hope I could remember. Sine x times cosine x. I told you already, we don't have a product rule for antiderivatives. It's going to be a while before we do. Okay? So that's not something we just know or have something for. But there is a way for us to take an antiderivative of that. Does anybody have Math 9? Math 9 will only give you a numeric derivative. If you have a TI-89, though, a TI-89 will get the job done. It'll take an antiderivative of that. There is a way that we can do it just using things that we already know, but may have forgotten. Yeah, no, there's no product rule yet. You could use maybe a Trig identity, yes. And we're not really expected to know double angle formulas, but I am going to do that for you because I have another point to make with it. All right, so I'm going to show you how to find an antiderivative for this thing. You're going to remember that sine of 2x equals 2 sine x cosine x. So sine x cosine x is equal to half of sine of 2x. Okay, so we need an antiderivative for half of sine of 2x. And at this point, we really don't know how to deal with the kind of the chain rule implications of taking an antiderivative. We don't really need to worry about it, because what we're going to do is we're going to get a hypothesis, and then we're going to test it, and then we're going to adjust our hypothesis until we get an antiderivative. Okay, so my first guess would be that the antiderivative was half of negative cosine of 2x, right? And so, y'all remember what you were supposed to do in Algebra 1 when you first started solving equations after that? You were supposed to maybe check your answer by plugging it in. That was I know that was a long time ago for y'all now. Yeah, but they don't know that. Okay, so yeah, you don't gotta be sorry. You just gotta think about the natural order. Okay, so what we're gonna do is we're gonna check that by taking the derivative. So f prime would be half of positive sine of 2x, but then we're going to multiply by 2 for the chain rule. And then that's going to kill off the half, and I'm not going to have what I wanted with being that. Okay, so I have to prepare for this 2 coming out for the chain rule by dividing by another 2. So I'm going to start again. Okay, so I'm going to maybe divide by 2 again. So I'm going to turn that into a fourth. And so now I'm going to take the derivative of my purported antiderivative, and I've got 1/4 of regular sine of 2x, then multiply by 2, and I have 2/4, which is a half, and so, I'm not sure what happened there. Now I have f prime is equal to 1/2 sine of 2x, which I showed is equivalent to sine x cosine x. Okay, so this could be an antiderivative, but that's a little beyond where we are at this point. We'll get there. We'll get a technique to deal with the chain rule stuff. Okay, the notation we're going to use for antiderivatives. Remember that for a derivative, when we're taking a derivative, we hit it with the derivative with respect to x operator. Okay, how we're going to undo that is we're going to say we're taking the antiderivative of 3x squared with respect to x. The with respect to x is important. Okay, it's actually multiplied by dx for reasons that we're going to see in the next unit. Really, it's because the area of a rectangle is base times height. But you can think of it as the antiderivative, the candy cane looking thing, and the dx are bookends that are, it's an operator on 3x squared. We're taking the antiderivative. Okay, here's some more antiderivative examples that I'm going to run through real quick because there's something else we got to get to today. Okay, so I'm going to increase the power by 1, so that's going to be x to the 5 halves plus 1 is going to be x to the 7 halves. We've still got this 2/3, and we're going to divide by 7 halves, and we're going to add c. That would be an acceptable place to stop, but if you wanted to divide by 7 halves, that's like multiplying by 2 over 7. So that's 4 over 21 x to the 7 halves plus c. And if we had more time, we would probably check that by taking the derivative and seeing that the derivative is 2/3 x to the 5 halves. Square root x. I didn't do any rule for square roots or radicals or things when we're taking antiderivative. But I didn't have that when we took the regular derivative. What did we do when we took the derivative of square root x? Yeah, we turned it into an exponent situation. So this is the antiderivative of x to the 1/2 with respect to x. So I'm going to increase the power by 1. 1/2 plus 1 is going to be 1 1/2. I'm going to divide by 3 halves, which is like multiplying by 2/3. And then I'm going to add c. What about the antiderivative of dx? Like, what do I even do with that? Okay, that's not so good to look at. What you're going to do is you're going to change that into 1 dx, right? Okay, antiderivative for 1 is going to be x, and then you have plus c. Over here, 1 over x squared. We don't have a quotient rule. What should we do instead? Yeah, make it a negative power. So it's going to be x to the -2 with respect to x. And so that's going to be, I'm going to increase the power by 1, and then I'm going to divide by the new power, which is just like multiplying by -1. And I'm not going to forget my plus c. Okay, so the same thing over here. So this is going to be 10x to the -4 with respect to x. And so I'm going to just go ahead and increase the power by 1 to -3. I've got 10, and I'm going to divide by -3. Over here, okay, I would tell you, do the heart-shaped thing, distribute or divide through by x squared, but someone yesterday suggested something I liked a little better. I'm going to turn the x squared in the denominator into an x to the -2, and I'm going to distribute it, which is really the same thing, but I think this is less error-prone than doing the heart-shaped thing. Okay, so that's going to be the antiderivative of x to the -2 times x to the 4 is just x to the 2. Plus 2x to the -2. And then it's already in that negative exponent form that's going to be really easy to use the power rule. So I'm going to increase the power by 1, that's x to the 3rd, divide by 3, that's going to kill off the 3. And then I'm going to increase the power by 1, so that's x to the -1, and I'm going to divide by -1, so that'll just turn that into a minus, and then I've got plus c. Okay, actually I've got 2 more. Okay, this one we need to rewrite in terms of trig, right? So if I have sine over cosine cubed, I could write that as sine over cosine multiplied by 1 over cosine squared x. Okay, what's sine x over cosine x? Tangent x. What's 1 over cosine squared x? What? That wasn't... Yeah, I did this wrong. This is not something that we have an antiderivative for quite yet, but we will. This is something we will in good time. That was, yeah, I think that was supposed to be cosine squared. Or, yeah. Yeah, because I wanted to be secant tangent so it could go up a level to secant. Anyway, and this one, what should I do with this? I'm gonna actually square it. So it would be the antiderivative of x to the 4th, 2x squared, and 4 with respect to x. And I trust that we know the reverse power rule well enough to carry that out. Now we're going to solve some elementary differential equations. Okay? So we're going to start by getting f of x. And we did this a little bit last time, I know. So it's going to be 8 over 4 x to the 4 plus 5x plus c. How am I going to find out what the plus c is? Because I need just an f of x. It's a real function, not some family of functions. Yeah, okay, so I'm going to use the fact that f of 1 equals negative 4, so that's negative 4 equals 8/4 of 1, or 2, plus 5 plus c. And so I've got 2 and 5 is 7, plus c is negative 4. That means c is going to be negative 11. And I can say that f of x is equal to 2x to the 4th plus 5x and the minus 11. Okay, maybe they give us the second derivative. Okay, we can do that. Okay, why don't y'all try that? And then check your work against mine. Okay, so you just take it one step at a time. You jump up a level and you go to f prime. And then you plug in to get get their value as c. Found that c was 1. Then I'm going to go up another level. And I'm going to have a different c. You can just keep calling it plus c if you like. If you're uncomfortable with that, you could call it c2, you could call it d, you could call it the, first letter of your first name, whatever you like. Okay, it's just some constant. Unless, your name is like Xavier or something. That would not be ideal, right? Or even like Yasmin might not be ideal. Okay, so here I've got one more. And I've got a second derivative, but it's in terms of trig. So let's just hop up a level and say, what's an antiderivative for sine x? This one's just commonly missed. That's why I'm counting on it in this lesson. Negative cosine, yeah, not regular cosine. Plus c. F prime of 0 equals 1, so 1 is equal to the negative cosine of 0 plus c. What's the negative cosine of 0? Negative 1, yes, unit circle. Practice it every day. So 1 equals negative 1 plus c. c is going to need to be 2. Okay, so that means that f prime of x is equal to negative cosine x plus 2. Okay, now I can say that f of x, I'm going to anti-differentiate. What would be an antiderivative for negative cosine x? Yeah, negative sine x plus 2x plus some other c. And then I'm going to use f of 0 equals 5. So 5 equals negative sine of 0 plus 0 plus c2. Sine of 0 is 0, yes. So 5 equals 0 plus c2. And so now I can say that f of x equals negative sine x plus 2x plus 5. All right, here we've got a particle motion problem. Remember, these aren't really any different from f of x. They've just got, you're given some context. Okay, so velocity is t squared. Position of the particle at time t equals 3 is 5. Find the position of the particle at t equals 2. Okay, we'll have a faster way of dealing with this in a couple of units, but for now, we're going to go up, we're going to write a formula for the position, and then we're going to plug in t equals 2. So right now, if v is t squared, x of t is the antiderivative of v of t with respect to t. So that's going to be the antiderivative of t squared with respect to t, and that's going to be 1/3 t to the third plus c. And I'm going to use that the position is 5 when the time is 3. So 3 to the third is 27. You divide by 3, that's 9 plus c. C is negative 4. Okay. So x equals 1/3 t to the third minus 4. What is the position of the particle at time t equals 2? X of 2 equals 1/3 of 8. So that's 8/3 minus 4 is 12/3, which is going to be negative 4/3. Particle has constant acceleration. So this is just where they're giving you the second derivative, right? And we're going to jump up a level. So v of t is going to be, if a of t is constantly equal to 4, that's what that means. V is going to be the antiderivative of a of t with respect to t. So that's going to be the antiderivative of 4, which is 4t plus c. Okay, so I used that after 3 seconds, after 2 seconds, the velocity is 1. So velocity is 1 when t is 2, meaning that c is negative 7. So v of t equals 4t minus 7. Okay, x, v is the derivative of x, so x will be an antiderivative for velocity. Okay, and that's going to be 4, we're going to increase the power by 1. It'll be t squared divided by 2, so 2t squared minus 7t plus some other constant. And we're going to use the fact that the position is 3 when t equals 2. So 3 equals 2 times 4 is 8, minus 7 times 2 is 14. And then I'm going to say, okay, so that's negative 6 plus c2 equals 3, so c2 will equal 9. So then I can say that the position function is 2t squared, negative 7t, and 9. Okay, so at t equals 2, position is 3. Wait, oh, no, I already knew that. Find the position of the particle after 3 seconds. So x of 3 equals 2 times 9 minus 7 times 3 plus 9. So that's 18 minus 21 is negative 3 plus 9 is equal to 6.